This is section 8, topic 4. It's called radical equations in the real world. And the target how do you solve literal equations involving radicals? So we've solved literal equations before. Remember, a literal equation is when you have more than one variable in the equation, okay? So when you have a literal equations, you don't solve them for like a number. You're just going to solve for the variable that it asks you to. And then on the other side of the equation, you could have another variable, 2 variables, 3 variables, whatever. You're just trying to isolate the variable that it asks you to. So you treat those variables just like you would if it was a regular old number. You would do the same operations, okay? We're still going to make room for our questions and key concepts. All right, here we go. A software programmer needs to write an algorithm a software programmer needs to write an algorithm for computing distance, comma, d, comma, using a formula that computes time t, I should say time, comma, t, comma, or actually period on the end of that. The formula for time t is shown below. And the formula is t equals the square root of 2d quantity divided by a. So that's a literal equation because I have more than one variable. I have 3 variables there. Currently, that is a formula that's solved for time. I could also solve for distance if I wanted to, or I could solve for a. I don't think it told us what a was equal to just yet. And it hasn't told us to solve for anything yet. It's just given us the formula, okay? What is the formula for D that the programmer will use to write the algorithm? what is the formula for D that the programmer will use to write the algorithm? So currently they've given us the formula for time that the software programmer uses to write the algorithm. They want us to write the formula for D, which is distance. So we have to solve for what? D. So I'm just going to rewrite my formula the way it was given. And the variable that they want us to solve for is under the radical. Okay, so this is a radical equation. We know how to do this, even though there's variables in it. It's okay. Is my radical isolated? Yeah. So, I mean, there's nothing outside of the radical. It's on the right side. Nothing else is on the right side except for the radical, right? Okay, so it's already isolated. So how would we undo the radical? Square it, right? We're going to square both sides. So, you know, in my notes, I like to show my steps. So I don't want to square it right on the original problem and then go back and look at my notes and be confused. Bless you. So I'm going to square both sides. So t squared is just t squared. And what do I get when I take the square root of 2d divided by a quantity squared? Just 2d divided by a. And I am solving for a. I am solving for d, but d is in the numerator of the fraction. Do I know how to clear the fraction? Multiply both sides by a, right? That's the least common denominator. We did that in our last lesson. So to clear that fraction, I'm going to multiply both sides by a. So on the left, a times t squared, we could either say t squared a or a t squared, it doesn't matter. On Algebra Nation, I think they put it in alphabetical, so they do a t squared equals, what's 2d divided by a times a? 2d. Solving for d, what's next? Divide by 2. So I get, I'm going to put my isolated variable on the left. D equals a t squared, or you could say t squared a is fine, quantity divided by 2. And can I reduce a or t squared by 2? No. Have I isolated the variable that they asked me to? Yes. Yes. Any questions so far? Okay. The programmer also needs to write a formula for acceleration A. So now we know what what the A stands for. The programmer also needs to write a formula for acceleration, comma, A. What is the formula for A? That the programmer will use to write the new algorithm. So we can either go back to the original equation that had where the t was isolated, or we can go to our new formula that we created where the d is isolated. So we have the formula for time, the formula for distance. Now we're going to write the formula for acceleration. It doesn't matter which one we go to. They're all the same formula, just written in a different way, right? I'm going to go to the distance formula since we've already kind of worked with the time formula, and I'll just start there. But you could use the original time formula. It doesn't matter. I'm going to go with the distance formula. And since I am running out of room, I'm going to work to the right instead of up and down. So we had distance equals a t squared divided by 2. This time we are solving for acceleration. So we want to isolate the A. But I can't do anything in that with the numerator until my denominator is gone. Multiply every term by 2 so I can clear that fraction, right? So now I have 2D equals AT squared. When I isolate the A, what do I do now? Divide by T squared. All right. So the A will be isolated. I'm going to go ahead and put that on the left side. So I had A equals 2D divided by T squared. Can I reduce 2 or D by T squared? No. Is my A isolated? Yes. So now the computer, the software programmer, depending on what information they've given, they have a formula for time, a formula for distance, and a formula for acceleration. Anyone have a question on that? Easy, right? So today, the lesson, that's all these are. Just giving you different real world scenarios and isolating for whatever variable it asks you to. So pretty easy because we know how to do all this stuff. So don't let the word problem confuse you. Give people a chance to catch up. Am I still writing? Yeah. Who can I give this to you when the... Oh, my thing's in your way. Yeah, and I'll let you take that. So I'm going to the next one. Oh. Is that what you meant? Thank you. Am I good? Are we good now? Okay. All right, next example. The average consumption of tomatoes by Italians, open parentheses, in pounds per person, between 1980 and 2000, can be modeled by the equation T equals the square root of 22y plus 275, comma, where T is tomatoes in pounds, no, 275, and that's a comma. Where T is tomatoes in pounds, and Y is the number of years since 1980. So the average consumption of tomatoes by Italians in pounds per person between 1980 and 2000 can be modeled by the equation t equals the square root of 22y plus 275, where t is tomatoes in pounds and y is the number of years since 1980. What equation can be used to calculate the year when a specific number of pounds of tomatoes were consumed? What do you think they're asking us to do? Solve for y, right? Okay. So I've got my original equation. Is my radical isolated? Yes. So I'm solving for y, which is under the radical. What should I do? Square both sides, right? Because the inverse of taking the square root is to square both sides. So, you know, I like to show my steps. So I'm going to rewrite the problem that shows me squaring both sides. So we know t raised to the second power is just t squared equals, what's the square root of 22y plus 275 quantity squared? Exactly. I'm solving for y, so what do I do now? Subtract 275 from both sides. And I get t squared minus 275 equals 22y. Now what do I do? Divide by 22. Now I can either, on the left side, I can do t squared divided by 22 and then negative 275 divided by 22. I can do that. Or I can just draw one big line so that they're both divided by 22. But you have to remember, both terms are being divided by 22. So if you're going to forget that, then just do it separately. Do t squared divided by 22 and negative 275 divided by 22. So now that my y is isolated, I like to put that on, I like my isolated variable on the left. On the right, I can't simplify anything. 275 does not divide by 22 evenly. If it did, I would probably separate those and divide that, but it doesn't. So that would be my equation for y, which is the number of years since 1980. That divides, if I did 275 divided by 22, I get 12.5. So if I wanted to write that as t squared divided by 22 minus 12.5, I could do that as well. Means the same thing. But I can't reduce t squared and 22. All right, so there's another part of this question. Does anybody have questions so far? Am I going too fast? Okay. In what year were 20 pounds of tomatoes consumed per person? In what year were 20 pounds of tomatoes consumed per person? What do you think we're going to do? Substitute 20 for T. T is the number of tomatoes, right? But T is just the tomatoes. T is tomatoes in pounds, and Y is the number of years since 1980. So what we'll do is we'll find the number of years since 1980, but it asks in what year. So we'll have more work to do after that. Okay, so we'll start with substituting 20 for T. And I can either go back to the original problem, or I could go back to the one we just created, which makes more sense since we're searching for Y and we know T already. So that's what I would do. And I'm substituting 20 for T. So that's Y equals 20 squared minus 275 quantity divided by 22. What's 20 squared, y'all? 400 minus 275 divided by 22. 400 minus 275 is 125. Divide that by 22 and you get approximately 5.68. So if that was your answer, in what year were 20 pounds of tomatoes consumed? In the year 5.68? No. That doesn't make sense, right? Y stands for the number of years since 1980. So about 1985, right? Sometime in the year 1985. Because it's a little over 5.5 years since 1980. So that's the year 1985. And if you need to explain why is it, the answer is 5.68, how do we get 1985? Does everybody understand that? If you think you're going to forget or make a mistake, make yourself a little explanation. Y is the number of years since 1980. So it didn't ask how many years, it said in what year. Okay, I've got two more problems for you. These haven't been brutal, right? Maybe writing all the word problems is brutal, but the problems itself, not too shabby. Everybody good? Can I move on? Okay. All right, next example. Isaac Newton discovered the way to calculate the minimum speed Isaac Newton discovered the way to calculate the minimum speed needed for an object to break free from the gravitational attraction of a massive body. This is called the escape velocity and it is measured with V equals the square root of 2gm divided by r, 2gm quantity divided by r, comma, where v is the escape velocity, comma, g is the gravitational constant, comma, m is the mass body, comma, and r is the radius of the body. What is the formula for r, the radius of the body? Bless you. All right, so we have this formula. It has a radical in it, so we've got a radical equation, right? And they want us to isolate which variable? R. They want to know the formula for R, so that means isolate the R. Is my radical isolated? Yes. So how can we get rid of, this is the square root, how can we get rid of that? Square both sides. So I've got v squared equals the square root of 2gm quantity divided by r quantity squared is just 2gm divided by r. How can I get rid of that fraction?
Or can you multiply it by r to make it easier?
I would multiply by r because Does 2gm divide by r? No, it doesn't, right? So it won't divide evenly. So I'm going to clear the fraction by multiplying each term by the least common denominator, which is what we did in section 7 test. And my least common denominator is, bless you, r. So I've got rv squared equals 2gm divided by r times r is just 2gm. I'll divide by v squared because the r is what I'm trying to isolate. It's now moved to the other side, but it's not isolated yet. It's multiplied by v squared, bless you. So if I just divide each term by v squared. So that gives me r equals 2gm quantity divided by v squared. So 2 is being divided by v squared, g is being divided by v squared, and m is being divided by v squared. Can I reduce any part of that? No. Anybody have questions? One more part to this example. What is the formula for m, the mass of the body? So we can either go back to the original formula for escape velocity, which is when the v was isolated, the formula for escape velocity. We could look at the formula that we just created for the radius. It doesn't matter which one we pick, they're the same formula, they're just in a different format. All right. So I'll just use the radius formula, and I will write a formula for the mass. So that's where I'm going to start. But again, if you wanted to go back to the original formula, that's fine. So in this example, we're solving for the mass, which is m. We don't have a radical, but we do have a fraction that we could clear by multiplying by the least common denominator of what? V squared. So v squared r equals, my v squareds cancel, and I have 2gm. Solving for m, what do I do? Divide by 2g. And these are just single terms, so I can do that. It's not a binomial, it's just a monomial. So on the right side, g divided by, or 2 divided by 2 is 1, g divided by g is 1, so 1 times m is just m. So I like to put my isolated variable on the left. And on the right, is anything gonna, can it cancel or reduce? No. Nope, so I just have v squared r divided by 2g. If I want to know the mass of the body, I take the initial velocity, square it, multiply that times the radius, take that whole quantity, and divide it by 2 times the gravitational constant. Easy. And then we will know how to calculate the minimum speed needed for an object to break free from the gravitational attraction of a massive body. See, just like that. No, we have one more. About the swing of a pendulum.
I thought you said we had 2 more.
Well, this was one. One example with 2 parts.
Okay.
Sorry. We have to talk about the swing of a pendulum. Everybody good with this one? Okay. See, if I didn't give you the word problem and I just gave you the formula, you wouldn't see how this related to the real world, you see. And then why would it be called radical equations in the real world?
Because we're in the real world right now.
Oh, okay. That's what I'm going to tell y'all when y'all say, when am I ever going to use this in the real world? I'm going to say, we're in the real world right now.
In this math class.
Right? All right, last one. The swing of a pendulum. Am I saying that right? Pendulum, pendulum, pendulum. measured in seconds, S, can be modeled by the equation S equals 2 pi times the square root of L divided by 32, where L is the length of the pendulum, in parentheses, in feet, period. Find the approximate length of the pendulum that makes one swing in 3.5 seconds. Round your answer to the nearest 100th foot. So the swing of a pendulum measured in seconds, S. So S is the time in seconds. Can be modeled by the equation S equals 2 pi times the square root of L divided by 32, where L is the length of the pendulum in feet. Find the approximate length of the pendulum that makes one swing in 3.5 seconds. Round your answer to the nearest foot. Okay, so did they give us a value for the length, or did they give us a value for the time in seconds? Time in seconds. So they gave us S, and they want to know L. So we could do this two ways. We could leave the equation like it is and substitute 3.5 for S or L. S, and solve for L. Or we could rewrite the equation, so instead of it being an equation for seconds, we could rewrite it so it's an equation for length, and then substitute in 3.5 for S. Well, to me, that's just making more work. Okay, but I think that's what they want us to do. I can do it both ways. I think it's just faster. Substitute in the 3.5 here and just solve for L. Okay, so I'm going to rewrite my equation. If we wanted to isolate the L, could we do that? Do we know how to do that? What would we start doing if we were going to isolate the L?
Get rid of the 2 pi.
How would we do that? Divide by 2 pi, right? Because 2 pi is being multiplied, but we're not going to do that. Or we could do 2 separate problems. We're just going to substitute in 3.5 for S. And solve for L. So we kind of would start doing that the same way as if we were isolating for the L. So if we want to solve for L, can we go ahead and square both sides?
No, you have to isolate the radical.
Right, so not yet. Don't square them until the radical's isolated.
So divide by 2 pi.
So this currently 2 is being multiplied by pi, is being multiplied by the radical. So this is one big term. So we just multiply that whole term by 2 pi. And then we multiply the left side by 2 pi. Okay? Did I say that wrong?
You said multiply or divide.
Oh, I'm sorry, divide both sides by pi. Divide by pi. So we have 3.5 divided by 2 pi equals, on the right side, 2 pi divided by 2 pi cancels, and we're left with the square root of L divided by 32.
Now we can square both sides.
Now we can square both sides. So on the right side, that just gets rid of the radicals. We have L divided by 32. On the left side, and be careful, so you can do this a couple different ways. Doesn't that mean that 3.5 is being squared, and 2 is being squared, and pi is being squared? That's what that means when you have a fraction with the exponent on the outside. Everything in there is being squared. It's a monomial. So me, I would prefer, I'm just going to go ahead and simplify all those things first. Okay? So 3.5 squared is 12.25. 2 squared is 4. And pi squared, there's a pi button on these calculators. Right here. Pi, we know pi is approximately what? 3.14. It's going to put in the, well, it can't put in the whole thing because no one knows the end of pi, right? But a lot more numbers. Squared is approximately, I'm going to go with 9.87. And since they want the answer in feet, I'm not going to leave it in terms of pi because it wants to know the actual feet. So I'm going to go ahead and change that to a decimal. So that is 12.25 divided by 4 times approximately 9.87, 39.48 approximately. And before I try to clear that fraction, I can simplify that. This is all in decimal, so I can do 12.25 divided by 39.48. And I get approximately 0.31. Now what?
Multiply both sides by 32.
Multiply both sides by 32. So on the right side, the 32's cancel, and I'm left with L equals. And since I still have this in my calculator, and I'm just going to leave it like that, times 32. And I get approximately, it says round to the nearest hundredth foot. So to the nearest hundredth foot, what would I put?
It'd be 9.93.
9.93, because 2 is in the hundredths place, so we look at the 9, it says round up. So L is approximately 9.93. Question said, find the approximate length of the pendulum that makes one swing in 3.5 seconds. So the pendulum makes a swing of approximately 9.93 feet in 3.5 seconds. Again, if I wanted to take my original formula for seconds and convert it into a formula for length and then plug in the 3.5 and solve that way, I could do that as well. The steps you would see would be very similar. Anybody have questions on that? Comments or concerns? Okay, I will freeze this for y'all while I stop my video.